Welcome to a screencast on energy and heat basics. If you light a match, or if you add ice cubes to a Coke to make it colder, or if you eat and digest and metabolize a hamburger, or if you drive your car to school or to work, you're dealing with a chemical or a physical process that involves energy changes as well as matter changes. Now to start, let's look at a simple physical example. And if we take a piece of iron that's been in a flame, we would say that it's hot. And what that means is the iron has a high temperature and the iron atoms are moving quickly. So if we look at this on an atomic level, we'd see iron atoms vibrating back and forth very fast. Now, on the other hand, if we have water that's been in a refrigerator, we'd say that it's cold. And what that means is that the water has a low temperature and the water molecules are moving slowly. So if we looked at this on a molecular level, we'd see water molecules moving past each other, but relatively slowly by comparison to the iron atoms. Now, all substances, like the piece of iron or the cup of water, has what's known as thermal energy, and thermal energy is the energy of motion of the molecules or atoms that make that stuff up, what's also called molecular kinetic energy. And that energy, the thermal energy, depends upon what type of substance we have. So for example, that it's iron. It depends upon how much of that substance we have, and it depends upon the temperature that substance is at. And so water would have thermal energy. That's going to depend upon the fact that it's water, how much water we have, and the temperature the water is at. And if we have two different substances and we place them in contact with each other, so for example, if we take the hot piece of iron and place it into some cold water, what we find is heat flows from the hot piece of iron into the colder water, and this heat flow continues until both substances are at the same temperature. And on a molecular or atomic level, what happens is when we place the hot iron in contact with the cold water, the fast-moving iron atoms bump into slower-moving water molecules, and they transfer some of their kinetic energy or energy of motion. And when this happens, the iron atoms go slower, the water molecules go faster, the temperature of the iron decreases, the temperature of the water increases, and this transfer energy continues until both substances are at the same temperature. And we would also say that they have reached thermal equilibrium, and this is always what happens. Heat always flows from a high temperature substance into a lower temperature substance, and that heat flow will continue until both are at the same temperature or until thermal equilibrium is reached. Now, the amount of heat that a substance will absorb or release depends upon several factors, and specifically, it depends upon the amount of substance, it depends upon the type of substance, and it depends upon the temperature change the substance undergoes. And there's a mathematical relationship between these quantities, and the equation is Q equals mc delta T, with delta T equals T final minus T initial. And in this relationship, Q stands for heat, which is usually measured in joules or in calories, and it's worth noting that 1 calorie is equal to 4.184 joules. M is the symbol for mass. We usually do mass in grams. C is the symbol for what's known as specific heat, which we usually measure in units of joules per gram degree Celsius or calories per gram degree Celsius. And then delta T is the temperature change, and typically we do this in degrees Celsius or in Kelvin. A quick note about specific heat. Specific heat is the amount of energy that's needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. And specific heat values can be determined experimentally They're found in tables, and metals, aluminum, copper, iron, for example, have fairly low specific heat because it doesn't take that much energy to change the temperature of a given amount of that substance. Water, on the other hand, has a much higher specific heat because it takes more energy to change its temperature for a given amount of substance. Okay, so let's put these together now and solve a question involving heat transfer between a piece of iron and some water. We're given the mass of the iron, its initial temperature, the amount of water, and its initial temperature, and we're told that they reach thermal equilibrium at an in-between temperature, which is sort of what we'd expect. And the question is to find the heat for the iron and the heat for the water, and to compare these values and explain the result. So let's start with the iron, and we'll use the equation Q equals mc delta T for the iron. And the values are given in the problem for the mass and the initial and final temperature. And the specific heat we can look up. It was in the previous table. And so when we put those values into the equation, the mass, 53.1 grams, given in the equation. The specific heat, 0.438 joules per gram degree Celsius. That's a looked up value. Final temperature is 23.1 degrees Celsius. Initial temperature is 84.7 degrees Celsius. When we perform this calculation, the grams in the degrees Celsius cancel, and we get a result of negative 1,433 joules. And if we round that off to the correct number of significant figures and put it in scientific notation, we have negative 1.43 times 10 to the third joules for the heat for the iron. Now, the value for Q is negative. What that means is heat is released or given off. This corresponds to the temperature of the iron decreasing. And this is always going to be the case when the substance has its temperature decrease. It's giving off heat, and you'll have a negative value for Q. Okay, now let's try the same thing for water. Q water equals mc delta T water. We're given the values for some of the known quantities, or some of the quantities in the problem, and then the specific heat of water is a look-upable value. We're going to use the fact that the density of water is 1 gram per milliliter, so 75 milliliters of water is 75 grams of water. Specific heat of water is 4.18 joule per gram degree Celsius. We looked that up. And then final temperature of the water is the same as the iron, 23.1 degrees Celsius. Initial temperature of the water is lower, 18.6 degrees Celsius. And when we perform this computation, we get plus 1,411 joules, rounding off to the correct number of significant figures, and going to scientific notation, it's 1.4 times 10 to the third joules. This is a positive number, so that means energy was absorbed, and this will be generally the case when we have substance increasing temperature, it's absorbing energy, and the Q value will be positive. And now let's compare. The Q for iron is negative 1,430 joules. The Q for water is positive 1,400 joules. And notice Q for water and Q for iron are pretty much the same value. They have approximately equal magnitudes, so they're both about 1,400 joules, but one is positive and one is negative. And they have opposite signs because the iron gives off energy, it's a negative Q. The water absorbs energy, it's a positive Q. And this is pretty typical for what would happen is when one substance gives off a certain amount of energy, the other substance absorbs that amount of energy. And in fact, if we have a perfect container that keeps all of the outside environment and away and prevents any heat transfer between anything other than the water and the iron, these two values will be identical. In reality, we don't have perfect what are called calorimeters or perfect containers, and there is some heat gain or lost with the environment, and so these values won't be identical in a real experiment, but ideally that would be the case. And that is it for the Energy and Heat Basics screencast.